Hello everyone, welcome to this video. In this video, we'll be looking at equality of two elements in a cyclic group. Are the two elements in a cyclic group always equal? Or what are the conditions when we have the order of element as finite or infinite? So let's see the conditions and look at this theorem. So this theorem tells us that if G is given to be some group, right, and A is any arbitrary element from this group G, then this element A has infinite order. If this element has infinite order, then in that case we say that element power I is equal to that element power j if and only if we have I is equal to j. So that means the two indexes, they are equal to each other whenever that element raised to the power is also equal to each other, and vice versa whenever we have the order of the element as infinite order. And whenever this order is finite, in we say the order is equal to n, right? In that case we say the subgroup which is generated by A is this set. What is this set? It is the set which consists of the identity element, right? A square and so on up to a to the power n minus 1 if n is the order. So that means you can write this E as a to the power 0 here, right? And moreover, these two elements a to the power I and a to the power j, they are equal to each other if and only if, in this case, when the case where the order is finite, right? So in this case, a to the power I is equal to a to the power j whenever this element n divides I minus j, right? So this is the theorem. So we'll be looking at the proof of this theorem. So let's see the first part here. For case 1, we assume that the order of this element A is infinite, right? If A has infinite order, in that case, let's see what happens. Then there is no non-zero n such that a to the power n is identity. Why? Because the order is infinite. So if you have a to the power n is equal to identity element, in that case the order would become n, right? And this n, that is finite in nature, but in our case the order is not finite, it is infinite. So therefore this thing won't happen here. A to the power n is not identity anywhere, right? So here we make this assumption that a to the power I is equal to a to the power j, and we'll be proving I is equal to j. The converse is very easy, right? For the converse, if you assume I is equal to j, then obviously a to the power I would be a to the power j, right? That is no issue, and that is the same element itself. So therefore the converse is quite obvious. So we just have to prove that whenever a raised to power I is equal to a raised to power j, then we have I is equal to j. So we assume that a to the power I is equal to a to the power j, and we have to prove I is equal to j. So if we have a to the power I is equal to a to the power j, so we can bring this thing to this side. So we have a to the power I divided by a to the power j, right? And what is it? By for division you could write it like this: a to the power I, a to the power minus j, that is equal to the identity element here, right? That means post multiplying by a to the power minus j on both sides. So the right hand side would become a to the power j multiplied by a to the power minus j. So this is the identity element, and so you can club up the powers here. So it would give you a to the power I minus j, and this thing is equal to e, and you can write e element identity element as a to the power 0. So that means you can equate the powers now. So I minus j is the power 0, right? So I minus j is equal to 0, and from here you obtain I is equal to j, the thing that you required here. For the next case, we assume that when A, the order of element, is finite, in that case your subgroup, this one, is nothing but this set, right? So we firstly have to prove this thing. So we assume that the element A has finite order, so the order of A is n, we assume it. We will prove that this set is equal to the subgroup generated by A, right? So we'll be proving this thing by proving that first of all this subgroup is contained in this set, and then we'll be proving that this set is contained in this subgroup. So from both of these containment we would have this equality here. So let's create this containment first. Now you know all these elements which are present within the sets, within this particular set, the element E, which the identity element, which you may write it like this, a to the power 0, right? Then the next element a, you may write it like this, a to the power 1, then a square, and then a to the power n minus 1. All the elements, they are powers of a, right? So they are definitely in the subgroup which is generated by a, right? Because that is the definition of this subgroup. So therefore whole of this set is contained in the subgroup which is generated by a. So let's mark this as equation 1. This was very simple, right? Now we wanted to make this containment the other way around. So for that, what we do, we take some element from here. So some element from here would be of this kind, a to the power k, right? Where k is any integer. It could be any integer. So we suppose that k, a to the power k, is any arbitrary member of the subgroup generated by a. Then according to division algorithm, we have some integer k, and we know n as our order of the element a. In that case, we wanted to make out whether n divides this k or not. So in both the cases, if it divides or if it does not, we may apply the division algorithm on it. So by the division algorithm, we may say that there exist integers q and r, they could be any numbers, right? Such that this k could now be written as q, the quotient multiplied with the divisor n plus the remainder r. So the remainder has to be less than this divisor here, which is n, right? So this remainder is either equal to 0 or it would lie between 0 or n, right? It is not equal to n or it is not greater than n in any case, because that's the division algorithm, right? So we have this condition on r. Now the element a to the power k, this could be written as, now because k is equal to qn plus r, so this a to the power k could be written as a to the power qn plus r, right? This thing, and then you can separate out the terms. So it is a to the power qn and a to the power r, right? So you can write a to the power qn as a to the power n raised to power q and a to the power r, right? And what is a to the power n? Because you know this n as the order of the element a, so a to the power n, so this implies a to the power n is equal to e according to the definition of order. So a to the power n is e, so we have e to the power q, a to the power r, and e to the power q is the element e only, that is identity only, right? And identity multiplied by some number is that number only, so you have a to the power r. So that means we started with a to the power k and reached at a to the power r, where what is r? R is a number which lies between 0 and n, and we have equality, we may have an equality at 0, right? Because r is some number which is less than n, so that means a to the power r should be some member of this set only. So that means a to the power r is a member of this set only, so it is present in this set. And what is a to the power r? It is nothing but a to the power k. So that means a to the power k is present in this set, and a to the power k was some arbitrary element of this subgroup which is generated by a. So therefore whole of this subgroup is contained in this set. So this is equation 2. So from here you may see that from equation 1 here, right, and from equation 2 here, we have the equality of these two, so that we have the subgroup which is generated by a is equal to the set containing e, a square up to a n minus 1, right?